So in the previous video, the boundaries were fixed and the equation was basically solved by simply moving the derivative into the integral and turning it into a partial derivative. So the next question is the case where the boundary is actually time dependent. So this is d by dt. A is still going to be fixed, however b depends on time. And there is again a function of x and t differentiated with respect to x. And this is going to be evaluated at t equals some arbitrary time t prime. The question is, what does this turn out to be? So evaluate time t prime. Okay. So basically, I'll look at this. So here's the function f. Now the function has some kind of shape. Actually, I'm not plotting f. So what I'm going to do is actually plot the motion of the boundary. So this is x equals the boundary. That's a function of time. And this is time. So the boundary is actually moving in time. So go to time t prime, it's here. And go a little bit into the past. Say at t naught, it's there. And slightly farther forward in time. This is at t naught. Some scale delta, which is a scale in time. So the important thing is that the derivative d by dt that is affected by the motion of the boundary, the derivative only takes place in an actually infinitely small time scale. So for starters, this time scale is going to be defined as this finite time scale delta. So basically, I'm going to make that a little bit thicker. So the derivative d by dt is evaluated on a small scale. Small scale delta. And this is a scale in time. So then I'm going to add some definitions. So basically, go back. going to define this location to be B naught. And basically do the following definitions. So basically B naught is going to be defined as the boundary at time 0, which is going to be a constant, since t0 is a fixed point in time. And then I'm going to basically define I go out to there, this actually has a width, delta. So there's going to be a B naught plus delta is going to equal B at T naught plus the delta in T. So basically the delta in T in time corresponds to a big delta in space, which is X. And then just define X prime is defined as B of T prime. And this is effectively a definition actually for delta. So another way to put this is delta is defined as B of T naught plus the little delta minus B naught. So basically these big delta and little delta basically define the width in space and time. So next thing to do is basically rewrite the integral. So here's this integral between A and B of T, which of course is just going to be this integral up top. So A of B of T, F X and T, and then dx, and then this is just by the definition of the limits of integration. This integral can be split up, so this goes to from A to B naught, f of x comma t dx, and that is added to the rest of the way, which is B naught to B of t, and this is f. So basically integrating on x, it goes to the integral simply goes up to the B naught, wherever that happens to be, and then it keeps going from B naught to wherever B of t is. So I'm just assuming by definition that B naught happens to be before wherever the boundary goes to, and I'm also assuming, of course, the boundary is increasing. The calculation would basically be the same if the boundary was going backwards, but this is going to assume that the boundary is increasing with time. Okay, so the next part is next thing to do is basically go ahead and differentiate this. Put equals there and do d by dt, d by dt, d. So this guy is now exactly what is up on top. And this part was just solved. So this is with constant boundaries. So all this is basically moving things into moving the derivative with respect to t into the integral and changing it into a partial. So d by t, function of xt, dx. So the rest of the work is basically going to be figuring this one out, which is this integral over this small integral distance in x. This distance is x is actually no more than delta, because b at whatever time only goes between t naught and this t naught plus this little delta, and delta is the maximum distance between hill and hill, therefore. So this is an integral over a fairly small region in x. So the question is, what does this integral turn into? So this is d by dt integral between b naught and b of t f of x comma t dx. Question is equals, what does this equal? So the concept is basically that, let's go ahead and that f of x can basically be turned into a 2D surface. So this is function of x and time, so this can be graphed in 3 dimensions. So basically this function of x and time will have some sort of shape in time, and basically the length coordinate, the spatial coordinate, and it will end up being some sort of shape in this 3-dimensional space. And since it's a shape in the 3-dimensional space, that means that if there's a point, here's the boundary that's going along there. Boundary is a function of time that's increasing with x. And there's this little area, so there's some point, this is basically the t prime point right there. And this is the area over which the d by dt is going to be active. So around this area, there's only this little distance in time, which is delta, and this little distance in space, which is big delta. So if this is projected upwards, it turns into some sort of object, cuts out a portion of the surface. And this portion of the surface is the only thing that actually matters with the integral. And it turns out there's a theorem in calculus that basically says that if this function is reasonably well behaved, as is in it's reasonably smooth and continuous, what's going to happen is the area around this point is going to actually, for f of x and t, is actually going to be a little plane. So f of x and t, located right there, can be approximated by a plane for the purposes of this integral. So going back over that, so we basically have this coordinate system. So I'm drawing the coordinates differently actually, but maybe I actually did not want to do that. I think I'll draw them the same way. So here's x and t, and so there's going to be some sort of surface that's going to approximate f. And in this surface, there's going to be a little point. So there's going to be a very little point, and this point is going to drop down and go to this point t prime. X prime comma t prime. So this interval will only take place over the point. So small area around x prime and t prime, f of xt can be approximated as a flat plane. So this is assuming this function is reasonably well behaved, which presumably it has to be, or this calculation will break down, basically. So